Let's get started. So last time we talked about was planted clique and random matrix theory. So who can give me a short rundown of what the main takeaways were from that class? Can you remind me what the planted clique problem is? Yep.
So first you generate a random matrix
Yep.
with each edge included with probability half.
Yes.
And then you plant in a large clique, and your goal is to find the
Yes, exactly. Now the question is, there it was an interesting example of a computational versus statistical gap, or so it seems, where how large does the clique have to be before you can information theoretically find it by some approach that doesn't necessarily run in polytime? Exactly. And yet the best known algorithms, what types of cliques did I find? So how big does the clique need to be? Right, but what about the polytime algorithms? So can anyone remind me some of the polytime algorithms that we covered? Square root A, exactly. So the main takeaway from last time was exactly for this planted clique problem, where we plant a large clique in a random graph. The clique is so large that there's no way that anywhere else in the random graph a clique that large could be there just by sheer chance. And the goal is to try and find it. So what we showed last time was we gave an efficient algorithm to actually find root n sized planted cliques. This improved upon this trivial degree counting method that just looked for the high degree nodes, that instead needed the clique to be root n log n. But the main idea in finding these planted cliques in these Erdos-Renyi random graphs was to actually use spectral techniques. So the main takeaway from last time was that if you think about the nodes in the planted clique and the edges that are in there because they're in the clique, then that's actually a rank 1 matrix. And yet we can think about the randomness on top as being some type of perturbation that we can show is small using random matrix theory. So what we're really given is we're given a perturbation of some type of rank 1 matrix that we can just use the top eigenvector to try and find which nodes actually belong to the planted clique. So the reason we only worked down to C times root n was because those were the types of deviation bounds we got for the corresponding random matrices. So that was the main takeaway from last time. Today we're going to do a really fun topic, one of my personal favorites, is compressed sensing. I think it's a shame to be an algorithms person and not know something about compressed sensing, at least enough to be dangerous. Has anyone heard of compressed sensing before? No? Yes? Oh, just a few. All right. So this should be a lot of fun. So, what I want to do before working up towards what the approach in compressed sensing is, the main focus is on a problem which is sometimes called sparse recovery. So the main problem that we're going to be interested in today is going to be the following type of optimization problem. Imagine what we're doing is we're looking for a sparse solution to a linear system. So here I'm going to use the zero norm, even though it's not really a norm, to denote the number of non-zeros. Given some vector x, it just spits out the number of entries in x that are non-zero. Your goal is to find the sparsest vector that solves some linear system where a and b are given to you. I'm going to call this optimization problem P0. So just to elaborate on this a little bit, what's interesting about this problem, I'm going to call this an n by n matrix throughout today. Now the idea is that, the idea behind this approach is that in many cases, there are actually many solutions to the plane linear system. For example, this would happen when n is much smaller than n. This is the so-called underdetermined case. So if I ignore this part about the number of non-zeros in x, then I really have a huge range of solutions that I could choose from, because I could take any solution to the linear system and change it by some vector in the kernel. But what we're going to do is when there really are many solutions to this underdetermined linear system, the goal is actually to, among them, find the one that's the sparsest. So this happens a lot, that a lot of cases you have many explanations for the observations you're given, but you look for some notion of the simplest explanation. In our case, the notion of simplicity really is the sparsity, so the number of non-zeros in X. So this is the optimization problem that we care about. It's called sparse recovery. But in fact, one of the major issues is that this problem is hopelessly hard in the worst case. So this problem is definitely NP hard. But what I'm going to tell you about today is that you can solve it anyways in really important families of instances. So even though this problem is hard, there are interesting examples of linear systems which really do arise in a lot of settings that you can actually solve this problem in a provable sense and actually find the best solution if there is a planted good solution. So the way that we're going to solve it anyways, so we'll solve it anyways using convex programming. And the approach that we're going to do is we're going to consider a related optimization problem where we're going to take what's hard about this optimization problem and replace it with something that's easier to get a handle on. See, what's hard about this optimization problem is the sparsity constraint on X. The zero norm isn't actually a norm, even though it has norm in its name. And we're going to replace it with an actual norm so that we really can solve this optimization problem. And I'm going to call this optimization problem P1. So what if instead, looking for the X, which is the sparsest, we look for the X with the smallest L1 norm, which actually solves the linear system. So I'm going to call this optimization problem P1. So what we really want to show today is we want to explore sparse recovery and understand what are natural conditions we can impose on A that actually imply the solution to this optimization problem really does recover the same thing as that NP-hard optimization problem that we wish we could solve. So the first question to you is it clear that this is a convex program? So who can convince me that this is a convex program? Yep.
Oh, it's a linear program.
It's a linear program. The objective function is a little different than what you're used to because it's an L1 norm. So can anyone tell me a little bit why this isn't a big deal? It might look a little bit strange. Why can I put a norm in there? Or who can cast this as an optimization problem that looks like a more traditional LP?
You just rewrite the L1 norm as the sum of the xi's?
Yes, the absolute values of the xi's, exactly. So what I claim is that what we can actually do, this convex program is completely equivalent to minimizing some sum of the yi's, or we think of these yi's as being a proxy for the absolute values of the entries in X. So what we're going to do instead is we're going to enforce that AX equals B, as usual. But now we're going to add in the constraints that X is component-wise bounded by Y, and that minus X is component-wise bounded by Y as well. So these two constraints, in turn, tell us that, in fact, the entries of Y are upper bounds on the absolute values of the entries in X. And the best you could ever do is, given some solution to this, you could choose the Y's so that each Yi really is the absolute value. Otherwise, you have some slack in this constraint. You could do better for your objective function. So this is just to convince you that this is honestly a convex program that we've already developed techniques to solve. What we're really going to focus on is why is P1 actually a good proxy to P0? So I want to give you a little bit of background about compressed sensing. There's an important term which you should definitely learn en route to these results, which is called the restricted isometry property. So I'm going to tell you what that property is and what are some results that actually show that under those conditions, really P1 does solve what P0 is trying to solve. But we're going to do a different approach than usual. We're actually not going to use RIP. We'll use something related to it. So I think it's the most pain-free way to do this. So let me try and answer the question now, or at least tell you something about what's known about when does solving P1 give a good solution to P0. So let me tell you about this really important property called the restricted isometry property. So we'll say that A has the restricted isometry property, which is usually abbreviated as RIP, with some constants, K and delta sub K, if we have the following conditions. For every X, which has at most K non-zeros, so its zero norm is at most K, we want the property that A on that vector behaves almost like an isometry, in the sense that the 2 norm of X is actually very close to what the 2 norm is of A times X. It should have upper and lower bounds depending on this delta sub K property. So this is the idea, is that the notion of an isometry, you can think about, what if A were something like an orthogonal matrix? So, what we'll really be interested in are A's which actually have many fewer rows than columns. That's where the wins come from studying these types of underdetermined linear systems. But if A were actually an orthonormal matrix, then A times X, the 2 norm squared, would just be equal to the 2 norm of X squared. So the constraint is that RIP is really asking that it behave like it's an isometry, but we only care about actually how it behaves on sparse vectors X. So the important thing is that there are actually matrices A that have this type of property that have many fewer rows than we would need if we really wanted A to be orthogonal. So if we wanted A to be orthogonal, it would have to be n by n, but we're going to get away with instead matrices that have many fewer rows than that. So does this definition make sense? This will be, one of the key things that we covered today.
Delta K is 0 and 1 things are 1. Delta K is small.
Delta K is small, so the actual theorem statements will require some bounds on what delta K is to be able to say things about when P1 is a good proxy for P0, but you can just think of this as a constant. So interesting RIP matrices will not be able to satisfy delta K as 0, but you should think of it as being something like 0.1. Yep.
So if you use, I think that was JL, you would get this, but not restricted, right?
So,
with enough rows.
yeah, with enough
so
rows.
with significantly more rows. Okay.
Yeah, there's actually a really strong connection between this and JL, which we're not going to cover.
Multiple really strong connections.
Which
The
we're not gonna
simplest
cover.
one being that any random.
We're not going to cover.
I mean, there's a really simple one, which is that
We're not
any
gonna cover.
randomized JL will, with high probability, be an RIP matrix if the number of rows is set correctly.
All right, yeah, that's true. Look, we'll get to that maybe later, probably not. But this is one of the important definitions. So I do want to apologize in advance that we're not actually going to use this condition because this isn't actually, I think, the easiest condition to study when P1 and P0 works. There's another related condition called almost Euclidean subspaces, which is intimately related to this, and that's actually the thing we're going to use. But for the time being, this is really something you have to know if you want to talk about compressed sensing because it's important in the literature. So what I want to do is give you at least a sample theorem of something that uses something like RIP in order to show that P1 is actually a smart thing to do. So let me give a sample theorem. So this is due to Candace and Tao. But really the development of compressed sensing should also be credited to Candace, Romberg, Tao, Donahoe, and so on. But this is a particularly clean version of it. So let's say that AX really is equal to B. It's hard to say something that P1 does something meaningful if the B that you constructed didn't actually have a planted sparse solution to begin with. So what we're going to do is we're going to operate in the setting where there really is a planted good solution. So there's some hidden X who, lo and behold, has at most K non-zeros, and is the thing which explains this right-hand side B. Now the question is, we don't know what x is, but we want to be able to find it under this type of promise. And then what you need is you need some like RIP-like constraint. I'm going to call this condition star, but let me write it out. Well, you need not only an RIP condition on k, but even an RIP condition up to 3k for this particular result to work. So if the sum of those RIP constants that you get from delta 2k, restricting just to 2k sparse vectors, and the RIP constant that you get from restricting to 3k sparse vectors, if those two things are small enough that they add up to something less than 1, well then it turns out that the uniquely optimal solution to P1 is a true x. So this is an amazing result because it tells us that actually, lo and behold, with this convex optimization problem P1, this is a setting where we're promised there really is a sparse solution, and we're promised that A has these RIP conditions, but solving this convex program recovers the true x underneath it. So let me elaborate on what's so amazing about this theorem and actually tell you a little bit more. Yep?
Is there intuition for why RIP is useful in this case when RIP talks about the 2 norm and this is the 1 norm?
So we will see that especially when we talk about almost Euclidean subspaces. So I prefer almost Euclidean because it has the geometry very explicitly. But almost Euclidean will actually literally say we're looking for subspaces, which will play the role of the kernel of A, where the 2 norm and the 1 norm behave almost the same. So we'll see that a bit later, but that's a good thing to keep in mind. Yeah?
Would this fail if there were multiple small x's of the solutions?
So B is generated by just one.
Oh.
So what we're going to show is that actually whatever sparse x generated that B, that actually under these RIP conditions will be the true thing that you find using this convex program.
So there can't be multiple.
Exactly,
x's of
because
the
that's
same-
actually implicit within the constraints of RIP,
Oh, okay.
that if there were two different sparse vectors that actually produced the same exact B, exactly, right? What that would mean is that the difference between those two vectors would actually be 2k sparse, and would actually be in the kernel of A, which would be a huge violation of this RIP constant.
Okay.
But that's great intuition because it tells you something about why you actually need control over slightly higher sparsity in order to say something. In any case, are there any other questions about digesting this theorem? It's a little bit of a mouthful, but it's a beautiful theorem. Let me try and pull it apart a little bit further because this theorem by itself is not quite useful because how do we even know there are good RIP matrices out there? So there are. Otherwise, this would be a much more boring lecture for you. And let me just tell you some of the facts that you should know about them, is that actually good RIP matrices are extremely common in the sense that if we take a random matrix, A, let's say, to be concrete, that you do something like you put independent Gaussian entries, but many, many other ways, almost every way you could think of choosing a random matrix A would work for this fact. And then you also have to scale it appropriately because you notice that I really need that the 2 norm of ax squared is close to 2 norm of x. So if it's close to some constant times that, I would really just need to rescale things. In any case, so when you scale this matrix A appropriately, then it actually will satisfy, let's say, this condition star, where these RIP constants, the sum of them is less than 1, with as few as m is theta of k log n over k rows. So, I think a picture really helps in this context. So what does this really mean? So the combination of these two things is very powerful because one tells us that, lo and behold, RIP is a condition that allows us to meaningfully find the sparsest solution to a linear system. And this fact tells us that there are actually many such matrices that meet that condition. But, what does the combination of these two things really mean? Let's at least draw a picture to see what's going on. Let's take our matrix A, which has the dimensions equal to this fact. So we should think about the number of rows as being C times K, log of N over K, and the number of columns as being N. So it really is a short, fat matrix. And lo and behold, when we multiply it by a vector x, which is itself k sparse, meaning that it has at most k non-zeros, and we create this vector of constraints b. So now you know A and you know B. Well, you actually can find what the true x was that actually gave you that B to begin with by solving this optimization problem P1. So what's interesting about this is that actually the number of constraints you have, how many pieces of information you get out from this B vector, is wildly smaller than the dimension of x. It's actually much closer to the number of non-zeros in x to begin with, off by a logarithmic factor. So what this means is that in a lot of settings, what you can do is you can recover structured objects. In this case, this means that it's a sparse object, it's a sparse vector, from many fewer measurements than there are actually dimensions of this high-dimensional signal. So this is actually a very powerful idea that goes a lot beyond just compressed sensing. But I want to tell you at least something about some of the practical applications of this. So one of the coolest applications is to MRI. So things like compressed sensing have actually had an impact that they've reduced the amount of radiation that you're actually exposed to in an MRI machine using these types of techniques down to 20% of what they used to be, based on actually taking fewer measurements and recovering structured objects in a more intelligent way. Sometimes it's also used in things like the single pixel camera. I won't really get into that, but this is a really nice marriage of theory and practice.
Although single pixel cameras are not quite practice.
Yeah, so practice refers to MRI. This one is more for writing grants. All right, so does anyone have any questions about the setup of compressed sensing and about the restricted isometry property? Yep.
So is the idea of compressed sensing that like you know what A is already and you measure B to recover X?
Yes. There are fancier versions of this where instead of actually knowing A, you can imagine being given many examples B1 through BP, which are themselves guaranteed to be sparse on some basis. You don't know that basis. That's another variant of these things that's studied, but that's much different than the techniques we're going to talk about. That's something called dictionary learning or sparse coding, depending on which community you're talking about again. All right, so what I want to do is I want to get to the technical meat, which is I want to make this transition from this restricted isometry property to something called almost Euclidean subspaces. We'll be able to get the same types of statements using almost Euclidean subspaces. And there's actually technical connections between them that you could really think about them as being different views of the same thing going on. So let me tell you what an almost Euclidean subspace is. And let me tell you at the outset that what the connection will be is that we'll care about the subspace, which is itself the kernel of this matrix A. What we're really going to do is we're going to develop these properties of the subspace being almost Euclidean, and then we'll just consider a matrix A which has that as its kernel, and we'll be able to develop these types of guarantees like an analog of the Candace Tower result, and even beyond that. All right, so what is an almost Euclidean subspace? So we'll say that a subspace gamma, which we think of it as living in n dimensions, but it has lower dimension. Well, we'll call it C almost Euclidean if for all vectors in the subspace, we have the property that it's 1 norm and it's 2 norm are themselves close after rescaling by root n. So this is the key definition. This just means that the subspace, actually the L1 and L2, can be wildly different norms, right? So if we think about a vector like V has 1 over root n everywhere, that's something which has 2 norm 1, but its L1 norm is as large as root n. And yet we can have wildly different things the other direction, like the standard unit vector, 1 and all zeros, has both its 2 norm and its 1 norm equal to 1. So in general, the L1 and the L2 norm can be off by as much as root n, and either in one direction. But what almost Euclidean says is that actually in restricted to subspace, they behave almost the same when rescaled by this 1 over root n. So what I want to do is first I'm going to draw a picture that's designed to capture what's actually going on, but then we're going to unravel what's actually going on in this picture. So this will be a hard picture to draw, so bear with me. So this picture is supposed to capture what it means for something we see almost Euclidean. Let's think about the ball of all vectors that themselves have L1 norm at most 1. So that ball itself in 3 dimensions just looks exactly like this, right? So we have vectors like 1 and all zeros, -1 and all zeros. We get these antipodal pairs, and we get that for all different coordinates. Now the idea is that this thing doesn't look at all like the unit ball of the L2 norm, because the unit ball of the L2 norm is itself a ball, right? So this really doesn't look like a ball at all. But the idea is that if instead we take some subspace of it and take the intersection, then in general what we're going to get is we hope that the intersection gives us a cross-section which is much closer to being a ball. And this is something which is absolutely true in high dimensions, that you can actually take this L1 ball and can take an intersection with a very large linear dimensional subspace and create something that geometrically very much resembles a ball within a constant factor of scale. So that's geometrically what's going on, is that we're looking for a subspace where actually L1 and L2 are roughly the same. Once you rescale by this root n factor, this factor of C really accounts for how much it's not a ball. So what I want to do now is I want to develop, let's say we had an almost Euclidean subspace. Let's think about what are some elementary properties of the vectors that belong to the subspace, and then we'll build up enough tools that we can actually prove things like Theorem 1, but in the context of almost Euclidean. So what I claim is that, and just to summarize this picture, what we really want at the end of the day is we want that this subspace gamma intersected with all x's whose L1 norm is at most 1 is itself close to being a sphere. All right, so let's do that. I'm gonna get rid of these things here, and let's develop some of the elementary properties. I'll tell you some basic facts, right? So almost Euclidean has 2 constraints on it, right? We have 2 inequalities. One of the inequalities is actually immediate and has nothing to do with the actual subspace in question. Which of those 2 inequalities looks immediate? The upper or the lower bound?
The lower.
The lower bound, right? Just to make sure we're on the same page, let me tell you why that lower bound holds, because we're going to use slightly stronger versions of this. Well, what I claim is actually for all vectors v, we have this inequality. This holds regardless of this subspace gamma. Now, this follows just by Cauchy-Schwarz, so let's prove it. Proof is obviously very short, which we can think about the L1 norm of V as being the inner product between V and a vector u, where u itself has the property that ui, its entry in the ith coordinate, is itself the sine of vi. So positive things go to +1, minus things go to -1, and 0 goes to 0. So this quantity here, then, just by Cauchy-Schwarz, is bounded by the 2 norm of v times the 2 norm of u, which itself is actually equal to the 2 norm of v times the square root of the size of the support of v. So if we take the number of non-zeros in v, and we take the square root of that, that's lo and behold what we get. So obviously root n is an upper bound for this quantity, and just rearranging that gives us this inequality, which now holds for all vectors. But I'm going to use the fact that we really could get away with a support here instead in what follows. So does this make sense? Good? Yeah?
Can you repeat the definition of support?
Yes. So support of v is just the set of I where vi is not 0.
So in this case, where we're considering the sign vector, we'd say sine of 0 is 0.
Exactly. Exactly. Right? All right. Yep.
So is support essentially 0 norm?
Support is the 0 norm. Yes. The absolute value of this, the number of coordinates in that, is exactly the 0 norm.
Support system.
Yeah. The support is the set, and this is just taking the size of the set. All right, so let's do it. So what I claim is, this is a kind of elementary property, but let's take this further, right? So what I claim, now let's actually get to some interesting things, which is, let's consider some v in this set gamma, which is non-zero, and let me set a particular value which will be useful for us. We're working with C almost Euclidean. Let me set this parameter s to be n over c squared, for a reason that will become clear in this lemma. This is one of the starting points of what's going on. So what I claim is that actually, if we have v in this set, and v is not 0, then the size of the support of v itself has to be at least s. So this will just be a rearrangement of this, but this is already crucial. Because this set, the subspace, is actually going to come from the kernel of our sensing matrix A. And this is going to tell us that there's no sparse way to actually go between two different solutions to the linear system. That's something that we need along the way. That's like your question about why can't we have two different k-sparse vectors yielding the same vector v. This type of condition tells us that we actually can't get away with two exactly sparse solutions. And ultimately, we'll have to build up even stronger properties to say that they can't even have smaller L1 norm going back and forth between them. But let's prove this. This is a very simple lemma. So we know that from above, we have the constraint that the L1 norm of v is at most the 2 norm of v times the square root of the size of its support. That's just repeating it. Now the important thing is that if we use the C almost Euclidean property, then we can replace the 2 norm of v with what we know its upper bound must be, which is C over root n times the L1 norm of v, and then we carry over the square root of the size of the support of v. And lo and behold, well, we can just cancel out this v1, this L1 norm of v on both sides, and then rearranging it, we're going to have root n over c over here. We square both sides, and lo and behold, we get that the support of v is at least n over c squared. So this is a really important property. This is something that you have to solve en route to finding an almost Euclidean subspace. Is your subspace better have the property that there's no vector in it whose support is actually little o of n, right? Otherwise you can't have this property of C almost Euclidean. So in fact, there's a nice way that you can think about this as being a type of generalization of standard coding results. So does this lemma make sense? Are there any questions about it? Good. So let me tell you a little bit of an analog. This is not really meant as a precise statement, but just for those of you who do know a little bit of linear error correcting codes, you can actually say that these things like almost Euclidean subspaces are almost like a real analog of what linear error correcting codes are over things like GF2. So in usual linear error correcting codes, we think of some code book, script C, as being the set of all vectors we can get, where we take an n by k matrix A, and we range over all of the x's in the set 0, 1 to the k. And we do this over GF2. So this is usually how you do error correcting codes, is you actually create what's called the generator matrix, and this gives you a way of taking a message of length k and turning it into a message of length n over the binary alphabet. And what you usually need for error correcting codes is that in order for them to have good properties like being able to decode them even after many errors, what you need is that all the non-zeros of these AXs have many ones. If there were some code word that actually had very few ones, then it would give you a way to actually corrupt just those ones and turn it into a different message, which would have been what you get when you encode the all zeros to begin with. So actually, this is why I like these almost Euclidean things, is it actually fits very nicely with some of the intuition about what's going on over linear error correcting codes. So if you don't know anything about linear error correcting codes, end digression, and we can actually continue developing some of the properties of almost Euclidean now. So let me develop what will be the key property now. I guess I need a little bit of space here. So this is the last property that we need until we can start proving recovery guarantees and showing that almost Euclidean is actually a good idea. So you can think of this as a slightly stronger version of the first lemma. Again, I'm going to consider some vector in this subspace, which better be non-zero. And what I'm going to do is I'm going to consider any old set T, which is a subset of the coordinates, which has the property that T contains at most S over 16 coordinates. Remember that S itself is n over c squared. Now the important thing that we're going to show is that V cannot have too much of its mass on the coordinates in T. So here what I mean is this vector V restricted to the coordinates in T. So what this is really saying is that no small set of coordinates, T, how small, and most S over 16 coordinates, can contain an overwhelming amount of its L1 mass of the vector, right? So this is actually the key lemma that's going to pave the way for actually doing recovery. So does everyone understand the statement of the lemma? It's a pretty short proof, yeah?
Restricted T just means with zeros everywhere, not T.
Exactly, exactly. So for example, yeah, we'll see more of that in a second. Are there any other questions about the lemma statement? Make sense?
So by the way, this lemma actually has an official name as well, or multiple official names. It's usually called the null space property, or sometimes the restricted null space property. Shows up all the time in
Yep.
basic sensing.
Yeah, exactly.
Why include delete if matters so much?
Why what?
Why include delete matters so much? Why it is? What is
I want to save that for, it'll be clear when we go to the theory. So let's take it for granted for the time being, but then when I actually use this, I'm going to emphasize what the intuition is behind it. It won't be clear until we actually get to that point, and I would find it confusing to give it to you right now.
Okay.
But thanks, so remind me to get to that. This lemma is actually very easy to prove, so let's just do it, and then we'll actually start talking about what its implications or why it is useful. So what I claim is that, we want to upper bound the one norm of Vt. So what else do we do but Cauchy-Schwarz? It seems that that's all we're doing today. So we know that it itself is at most root t times the 2 norm of the vector Vt. Now this in turn, well, the 2 norm only gets larger if we consider all of the different coordinates. So lo and behold, we have this inequality. That's fine. Well, we've used Cauchy-Schwarz. There's only one other thing we can do.
Use Cauchy-Schwarz again.
I guess that's something else we could do. Well, we haven't used C almost Euclidean. That seems kind of necessary to prove this. But let's use C almost Euclidean. Using the C almost Euclidean property, lo and behold, we can upper bound the 2 norm of this vector v. That's exactly why I forgot about the fact that it was restricted to t, was just that I could turn it back into a vector in my subspace. And lo and behold, now we can plug in our upper bound on what t is. T is at most n over 16 c squared using the way that we've set s, and we get the 1 norm of v. And then everything actually cancels nicely. So we get exactly what we were looking for, which is the 1 norm of v divided by 4. Right?
In
Yeah.
the theorem statement, the size of t is s over 16. Where did the c squared come from?
So s, I'm going to use that throughout, is s is set to be n over c squared,
Okay.
because that'll be always the parameter that's going to show up for us. So it's saying, we got to say something in lemma 1, which actually had the constraint just that we got that the support was at least n over c squared. Here we're taking a step back because instead of s, which is n over c squared, we're considering s over 16, but we're developing a stronger property because not only does it have many non-zeros, but in fact their L1 norm can't be too concentrated on just a few coordinates. So that's the idea, right? So it's kind of like a qualitatively weaker thing where we took a step back on the actual sparsity we're considering. But in fact, I claim that this lemma is now almost there. We can actually prove a recovery theorem, which is going to show you a little bit about why almost Euclidean comes up at all. So this will be the first main theorem statement that we proved today. It's actually a very short proof again. Let's do it. So now, finally, we're going to consider this optimization problem P1 that we introduced at the very beginning. So my claim is that, if again, we start off with this promise that AX equals B for some X, which has at most S over 16 non-zeros. Remember that this quantity right here is the same thing as n over 16 c squared, just based on how we've set s. Well, and we also want some almost Euclidean property, but as I mentioned, that constraint is going to be on the kernel of A. So we want that the subspace we get from taking the kernel of A is itself C almost Euclidean. Then what I claim is that X is the uniquely optimal solution to P1. That's a type of thing that we talked about before with things like the restricted isometry property, was that when you have an RIP-like condition, in that case it was delta 2k plus delta 3k is less than 1. In this case, it's a constraint on the kernel being almost Euclidean. Under that condition, and the constraint that you have a planted sparse solution, what you recover from P1 is actually the true sparse solution that's planted.
Are these equivalent conditions?
Almost Euclidean and RIP,
Yeah.
they're morally equivalent. There's some technicalities, so we're not going to get into that. And RIP, I think you should know the statement of it just for posterity's sake, because many results are stated that way. But I think this is a pretty convenient way to develop some of the theory. All right, so in fact, I promise this proof is not long. We've already used all the tricks we could hope for. Well, what are we going to do? And this is where some of the intuition behind lemma 2 is going to come into play. Suppose not. So I'm going to let W be the optimal solution, which, our theorem was wrong, and lo and behold, we found something else that was the optimal solution. And we know that how the solution we find via P1 differs from the true solution, it has to differ by some vector v that is in the kernel of A. Just because W and X both solve this linear system, AX equals B, right? And as one more piece of notation, I'm going to let T denote the support of X. So here's the idea, is that X itself, let me tell you the intuition, that way it's clear what's going on in the math. The idea is that X is sparse, right? And we know that V is a vector which is almost Euclidean. So we know by lemma 1 that it can't have too much of its L1 mass concentrated on where X is non-zero. So when we look at the L1 norm of W, worst case scenario, in fact, V contributes in all the places where X is non-zero to decreasing the L1 norm, but outside of where X is non-zero, it has to contribute to increasing it, and it increases it at a higher rate than it decreases it, and hence, it's actually a worse solution. So the rest of it will actually just be following through on this plane, but that's exactly what the intuition is, and that's why lemma 2 actually comes into play. So let's do this. It's just a few inequalities now. So let's look at the L1 norm of W. After all, what we want to prove is we want to prove that the L1 norm of W is strictly larger than what? The L1 norm of X, right? Because that would contradict our assumption that actually W is the optimal solution. It would say that when you think W is the optimal solution, this would be a proof that no, X is actually better than W, right? So we can write this out now as the L1 norm of two different vectors, W restricted to T, and what else? W restricted to the complement of T. That's just an equality. But now the important thing here is that we can actually lower bound what this L1 norm is, that we get some contribution from the T part, which could be as little as this quantity. So the contribution from the T part, WT, the L1 norm of WT, worst case, we get the L1 norm of XT minus the L1 norm of VT, because V just happens to reduce all along the places where X was large. But we also get a contribution from T complement, because on T complement, X is 0 just by construction, whereas V is non-zero. So that's something that cannot be compensated for. It really does contribute to the L1 norm of W. So this is the key inequality. Does this make sense to everyone? Yep. This is just saying that this term is lower bounded by this, just by triangle inequality. And this term is actually equal to this because XT complement is actually 0. It has 0 in all of its coordinates. So now we're in business, right? Because at the end of the day, what we can do is we can write this out now as being the one norm of x. After all, xt, the one norm of that, is exactly equal to the one norm of x because t complement has nothing in x. And we can rewrite this term in a slightly more convenient way. What I can do is I can subtract off an extra vt1, and I can add back in the L1 norm of v. So here I had vt complement, and here I had vt. So what I'm doing is I'm subtracting an extra vt so that I can add back in the vt, and lo and behold, those two terms give me the L1 norm of v. So now we're actually in great shape. Can anyone tell me why we're in great shape?
That thing is at least half with the.
Yeah, exactly. So here's the idea.
I'm sorry.
No, you're right.
Or, well, I was pointing to a particular thing, but if I pointed to a different thing, I would have been right.
I see. There was something in there that was correct. So what I claim, just to finish off this proof, we know that V is actually in this kernel. That's the way we constructed it. So what I claim is actually just massaging what lemma 2 is. What we really know is that the one norm of V minus 2 times the one norm of Vt is itself at least the one norm of V divided by 2. That's just a rearrangement. If we pulled this on the other side, we would have half times the one norm of V. And then we then we divide through by the 2, and we get exactly this factor of 4 that we needed in there. So what this means at the end of the day is that what we get applying this is that this itself is at least the one norm of x plus the one norm of v divided by 2, which is strictly larger than the one norm of x because v is non-zero. So that's it. It's actually a very short proof once you have almost Euclidean that actually this optimization problem P1 recovers an exactly sparse planted solution perfectly. Questions about this theorem? Make sense? Cool, not cool? Yeah?
Did we ever use lemma 1?
Did we ever use lemma 1? No, not really. This was just to develop some intuition for this.
Lemma 2 is basically like more or less strictly stronger.
Exactly. So the only thing that's slightly weaker about lemma 2 is the statement that we're instead considering S over 16. But you should think of it as a qualitatively stronger statement because not only does the vector have to have many non-zeros, in fact, those non-zeros have to have, can't contain a huge fraction of the L1 mass. So that's the idea. But lemma 1 is itself something interesting to know just for the purpose of this analogy with error correcting codes, that a prerequisite, but something that doesn't apply almost Euclidean by itself, is that you better have that in your subspace there are no little o of n sparse vectors. That's actually the same constraint that you need for linear error correcting codes. It's just that almost Euclidean is a slightly stronger property because of how lemma 2 is actually qualitatively stronger than lemma 1. Yep?
Lemma 2 could have been, we could have replaced 16 with k squared, or an arbitrary number squared.
Yes.
That looks more obvious.
Right, I mean, we still would have had to lose something compared to the thing that we actually proved for this.
Okay.
But, we could have lost a smaller factor for sure. All right, so what I want to do actually is, so are there any, I'm curious, do you guys have any philosophical objections to this type of statement? I mean, this is, at the face of it, pretty cool. It says an exactly sparse solution. You can recover with much fewer numbers of measurements. I guess I should also tell you what's known about almost Euclidean subsections. So let me at least state that as a theorem. And then we can tie it all together. So the same way that I asserted that a random matrix with the right dimensions is actually RIP, well, actually can prove that a random subspace is actually almost Euclidean. So this work goes way back to much before compressed sensing. It was studied within the functional analysis community, usually credited as either being Kashin or Garneev and Bluskin. This was in the 60s, this was in the 70s. And it turns out that a random subspace, actually for many notions of random, for example, you could think about generating it as the kernel of some random matrix. Well, a random subspace in Rn, which has dimension n minus m. So the reason I'm using these as the parameters is because remember that in compressed sensing, we thought about it as having an m by n matrix, where we wanted a really short and fat matrix. So if this is actually the kernel of that, we should think of its dimension as roughly being, what its original dimension was, minus the number of rows in A. So we get n minus m, just to keep things simple. Well, then the claim is that it's C almost Euclidean, with C being about root n over n log of n over n. And this holds with high probability, with overwhelming probability. So just to put this in perspective, let's think about what this means now. So my claim is that, at the end of the day, what theorem 2 implies, plus this result, so this tells us that a random subspace is good. So we would just take our matrix A to be the matrix with this as its kernel. Well, and then theorem 2 tells us that such things are actually good for sparse recovery. What the combination of these things tell us is that we can actually do sparse recovery, so we can obtain sparse recovery. Up to the zero norm of x, which is itself s over 16 in our theorem, which is the same thing as n over 16 c squared. That needs to be about m over log n over m. So this is exactly the types of guarantees we talked about to begin with, which is that if you had some vector which was k-sparse, how many linear measurements would you need of it? You need roughly that number of measurements to begin with. So if you started off with m linear measurements, you could obtain things which are almost as sparse as the number of linear measurements you have to begin with. So it's actually the same type of theorem statement. So the combination of these two things gives it. So are there any questions about this? Yep.
How does that compare to just the number of sparse vectors of that size?
It's log of it.
Okay, so this is like about, roughly, it's like close to perfect.
I'm cautious to say that because that's not a formal argument for why this is a lower bound. And a lot of people have mistakenly thought it is, but it's not, and you have to do a bit more work to actually show lower bounds meeting this.
Okay.
But these are all tight, all of these results. Cool, all right. So actually I'm curious, does anyone have any philosophical objections with these types of things? See, these aren't the strongest types of recovery results that are out there, because there's a really important caveat to why these things would or would not be practical. Yep.
Well, it all depends on what system is generating your...
That's true. That's why I said MRI is a great example, is because you have the control over how you perform the sensing on the vectors. That's important, is because, compressed sensing is only as powerful if you actually get to choose that, or if some reason for believing it's random to begin with. Was there another hand that I saw? There's another elephant in the room in this. Let me ask my TAs then. Well, okay, let's go with non-TAs first.
How hard is it to compute C?
How hard is it to compute C? As in, okay, that's a great question.
Doing A
Yeah.
times C.
So as far as we know, it is hard to compute C, and it's also hard, given a matrix, to decide whether it's RIP or not. But actually, we don't technically know that that's hard in interesting ranges of parameters, so it's a separate question. It's actually something that people have been thinking about research-wise. There's one other elephant in the room.
With like information theoretical?
No, not that one. That one's all right, I think. I mean, when do you actually have an exactly sparse vector? Seems like never, right? See, what makes compressed sensing actually powerful is the fact that it actually continues to have guarantees, even when you're given noise.
Although
AX is not.
Unfortunately, the exact algorithm that you mentioned does not quite work because
Yes. Yeah, exactly.
you're looking only for things that exactly satisfy AX.
Exactly.
So, this can be seriously
So I'm going to
satisfied.
sidestep it in a slightly different way, which is I'm instead going to study what happens when X's are not exactly k-sparse. You can think about that as a type of noise on top of being k-sparse. There are other things that actually work for really honestly additive noise, but this is also a pretty simple one to do. So what I want to do in the time remaining is actually, it's kind of just a variant of theorem 2, is that a slightly longer version of this proof is actually going to give us some pretty cool guarantees that work even when X is not exactly k-sparse. So let me tell you about that. Let me tell you first the setup for this. The same basic ideas of almost Euclidean that we've developed will actually work verbatim. So that's great. So let me cast a new type of problem. So what I want to study is what happens if X is not exactly k-sparse. We should think about it as maybe X would still have k large coefficients, but there's a, all the other coefficients might themselves be non-zero. They might just have small values. So what I want to do instead is I'm going to introduce a piece of notation. Let me call it sigma k of X, which will be the min over all W, which are k-sparse, of the L1 norm between X and W. So this is some type of measure of how close you are to being k-sparse. So if, for example, X were exactly k-sparse, then sigma k of X would be what? 0, right? So in fact, this is something that's going to smoothly change as X moves away from being exactly k-sparse. Let me tell you the theorem statement. So this is a cool generalization of the things we've studied so far. So this sort of noisy setting, although dealing with real additive noise is a little bit more of a pain. So I'm going to let AX equals B, again. We think of X as being the planted solution. And again, we're going to have some constraints on the kernel of A, that it be C almost Euclidean. And again, I'm going to use this parameter that makes everything work. N over C squared will be my S. And what I claim is that if W is the optimal solution to P1, this convex program we care about, then actually W really does have some meaningful guarantees that the one norm between X and W is at most 4 times the value of sigma at S over 16. That's. So what I claim is that, what's important about this, so can anyone tell me why theorem 3 is actually a generalization of theorem 2? Just to impress upon you the fact that it's already powerful, yeah?
Well, if sigma sub S over 16 is 0, then the difference will be 0 and we'll have the exact
Exactly.
solution.
Exactly. So this is a version of theorem 2 that actually applies much beyond the setting where we originally studied it, where X was exactly k-sparse, for k being at most S over 16. It implies exactly the same thing that you get perfect recovery when you are perfectly k-sparse, but it also tells you something interesting even when you're only close to being k-sparse, and that you have roughly small number of coefficients that cover most of your mass. Yeah?
So before we, I'm trying to think of the difference between having less than S over 16 before and having, and we're only talking about S over 16 now, means it's any weaker, but I don't think it is.
I don't think so. Yeah, I think it's literally a generalization of theorem 2. I could have been more tight with my parameters in theorem 2 and gotten something a bit better, but that's a separate issue. Any other questions about this? This is all that remains. We're going to prove this. Yeah.
On the bottom right, is that sigma sub quantity S over 16 or
Yes.
sigma divided by 16?
Sigma sub S over 16. So that it's really like sigma sub k, where k is S over 16. That's why it's a generalization of theorem 2. All right, let's do it. This one will be a little bit more clever than theorem 2's proof. Actually, let me leave that here. Instead, I'm going to do it over here. I have to erase my beautiful picture, though. So let's prove it. And essentially, we're going to try and mimic the proof of theorem 2. So we started off with, t being the support of x. Instead, what I'm going to do is I'm going to let t be the S over 16 largest magnitude coordinates of x. So already it is a generalization of theorem 2, that step, because t was otherwise the support of x, which if x were exactly k-sparse, would have gotten exactly the same thing. So what we care about now is we care about the L1 norm of x minus w. So x is our planted solution. W is the thing that P1 finds. We want this guy to be not too large, because that's what our theorem stipulates. So lo and behold, let's do the same exact trick of breaking it up into its contribution on t versus t complement. Nothing fancy going on. And now what I'm going to do is I'm going to upper bound this using the triangle inequality. I get exactly this term, which I had before, but I'm going to have xt bar 1 norm plus wt bar 1 norm. All right, so now I'm actually going to do a little bit of manipulations to get this to be a nicer form than it is. So what I claim is, the same type of trick. One trick that I used last time was actually adding in things like wt sub 1, so that I could pair it with this and actually create w1. I'm going to do the same types of things, which is that I can rewrite wt bar 1 as being the 1 norm of w minus the 1 norm of t. But now I better use somehow the fact that w is the optimal solution to P1. So what I claim is we know something about the 1 norm of w. What do we know about it? Can we bound it by anything interesting? The 1 norm of x, right? We know that since we found w and not x, x was a perfectly good solution to the optimization problem P1. Well, the fact that we found w means that w is better when judged by the L1 norm, or at least as good, because w is optimal for this convex program P1. So at the end of the day, what we're going to get, putting this all together, is we're going to get that the L1 norm of x minus w is in fact upper bounded. Well, I've got this first term right here. That's going to stay exactly what it was supposed to be. And I'm going to have the remaining terms. I have this xt complement carried over, plus this, now I'm plugging in for what my bound is for wt bar. I get a x is 1 norm, and then all minus wt1. So this is the new inequality that I'm getting to. So one more step and then we'll actually be in great shape. So let me tell you what that step is. So let me actually introduce some, to reduce my amount of writing. Let me just call this star. And what I claim is that now, star, we can do the same type of rewriting as before. It doesn't really look like we're making progress, but I claim we are. Which is I can do the same thing where I pull out an xt complement 1. But now what I get left over from this x1 norm is I get some extra xt's 1 norm, and I still have this minus wt's 1 norm. So now the last inequality that I need in here is I claim that this entire thing is now, well, we have two subscripts of t, so we can actually pull them together using the triangle inequality, and we get that this is upper bounded by x minus w on t. So now, actually, all I'm going to do is I'm going to put everything together, and it'll just fall out from it. So let's collect what we figured it out, and let's put it all together. All right. So at the end of the day, what we wanted to bound was we wanted to bound the L1 difference between x and w. And we had this first term, x minus wt sub 1. But lo and behold, I picked out two of these terms and got another one of those terms that goes along with it. So I get that this quantity is at most 2 times the L1 norm between x minus w, restricted to the set t. And I still have some leftover terms, which are just this guy now, right here. And this is t-bar. All right, so now I claim one of these terms is actually nice. So can anyone give me another name for this guy right here? We're in good shape.
That's just sigma s over 16.
Perfect. Exactly, right? So this quantity right here, that's exactly why we wanted to pull this out, is because this is something that needs to go on the other side, is this is exactly this quantity, which is how much L1 mass is off the largest s over 16 coordinates. That's how we chose t to begin with, is actually to pull out what the largest coordinates are. And now, this quantity right here, we better use our lemma 2. That's actually one of the main things that was used in the proof of this theorem 1, was that we used this lemma to actually show that for vectors in the kernel, that we can actually bound how much L1 mass they associate to a small coefficient. So where should I use lemma 2? Which of these, can anyone tell me a little bit about why I should be able to use it? So x minus w is in the kernel? Yes?
Yep.
So then, again, I'm back in the same situation where I have a vector that's in the kernel, and I'm looking at how its L1 mass behaves on a not too large set of its coordinates. So what we can do is, again, now by lemma 2, and then we're done, is we can bound this quantity by x minus w's 1 norm all over 2. I'm really capturing this extra 2 in here, because I have that I can bound it divided by 4 as a result. Now we're in great shape, because all we have to do is we pull this on the other side, and lo and behold, we get our factor 4 in front of this sigma s over 16. So that actually finishes the proof. That's it, right? So this is now the analysis of what compressed sensing does, what replacing an L0 norm with an L1. So just to recap what's going on. at the end of at the beginning of the lecture, we started off with, we wanted to solve sparse linear systems. We wanted to find the sparsest solution. That was optimization problem P0. That was hopelessly non-convex, and it really is NP hard. But once we have these conditions on A, either through the restricted isometry property, or through the fact that its kernel behaves like an almost Euclidean subsection, that's enough geometry that we can actually show that P1 is actually a good approximation to solving P0, even though we can't. So our first result was actually an exact recovery guarantee that when there's a planted good solution that really is sparse, we can actually recover it exactly using P1 with roughly as few measurements as there are number of non-zeros in X to begin with. This last theorem is actually a vast strengthening of it because it tells us something interesting that works even when X is not exactly K-sparse, but has K large coefficients that contribute the most to it. So I want to tell you just a little bit because, we're obviously not going to get to any of these later topics. But, taking a step back from what's going on is this is really one example about, what we covered today was just one example of recovering structured objects. So in this case, our notion of structured was a sparse vector, and we wanted to do it from few measurements. In this case, there were even linear measurements. So this type of philosophy can go a lot further because we can also study things like, one of my personal favorites is something that's called the matrix completion problem, where you can imagine that what you're given access to are random observations of the entries of some low-rank matrix. So actually, one of the places where this comes up is in what's called the Netflix problem. So you want to be able to predict how much different people like different movies that they haven't rated. You could think about some matrix which describes for each user how much they would like each given movie. And the usual assumption is that this underlying matrix, if you coerced everyone to review every single movie in Netflix, would be somewhat close to low rank. You can again ask the question of how few observations do I need to be able to meaningfully reconstruct the underlying matrix. That's actually just a generalization of some of these ideas of compressed sensing. And there are many other examples. You could take an entire class on these types of things. So just to give you some keywords, there are things like phase retrieval. If you're curious, you can ask me about any of these after class. There are things like sparse PCA, where you want to decompose a matrix as a sparse matrix plus a low rank one. There are even things like tensor completion. So this idea of actually taking many fewer measurements than the intrinsic dimensionality of the problem is actually quite powerful. This is just the very beginnings of it. All right, so that's it for today. So if you guys have any more questions, I'll take them offline. Otherwise, we'll be covering on Monday as we'll be continuing our, rapid tour of algorithms, and we'll be doing smooth analysis. So that'll be another fun topic. All right, see you guys.